From ContainerDays Hamburg, this video is proudly presented by DAX IT.
Hi, and welcome to my presentation about Kubernetes networking horror stories, where we will discuss issues from actual customers. We will discuss how we can debug such issues, and in the end, I will also provide you some best practices so that in the best case, you do not even run into those issues in case you run Cilium on top of your Kubernetes cluster. So, my name is Philipp Schmid. I'm a solution architect, part of the post-sale team, which is called Customer Success Team at Isovalent, and now for about 1.5 years, part of Cisco. Let's first clarify a few assumptions here, as this is for sure not a Cilium 101, and it's for sure also beneficial if you have some basic understanding of Kubernetes networking. Now, the three shown horror stories are based on actual customer issues, but obviously I can't share customer names or specifics about their environment. That's why I also used a reproduction environment based on kind to kind of simulate the same failure behavior. And with that, I was also able to basically share all those reproduction steps with you in this public GitHub repository, in which I also share all the slides and including a fourth horror story for which we most likely won't have time during this session itself. So feel free to take your phone out, scan the QR code, so then afterwards there's no real need to take pictures of slides as you have all of them available there as PDF. Let's talk about the first story, which I called Everyone Wants an IP, and usually also the correct one. Now, what do I mean by that? Let's assume you set up a Kubernetes cluster. It doesn't even matter too much like which Kubernetes flavor you choose. Let's assume, for example, on the left-hand side, we have a kubeadm cluster, or on the right side, we have a kind-based Kubernetes cluster. And in the end, your goal is just to configure a specific pod size range for this particular cluster. As, for example, you want to make sure that it's not overlapping with any other IP ranges from within your network, or that it's not overlapping with other Kubernetes clusters you might have. Now, if you install Cilium on top of that with its default configuration, and you have a look at the actual pods by using, for example, kubectl get pods-o YAML, you suddenly see that the pods get an IP from a different range, which isn't even part of this 10.11.0.0/16. Now, to understand where does this come from, we need to understand like how Kubernetes usually does pod IP assignments, or like dedicates the ranges for the pods that are scheduled on a particular node, and compare that to how Cilium does it out of the box. Now here on the left side, we see how Kubernetes does it, and we see that it's basically just another flag on the well-known node resources, and those are the resources you usually also like get if you do kubectl get nodes. So it's just another flag there. We also see it in plural form, so podsiders. That's added that was added when IPv6 support was added to Kubernetes as well. As if this would be a dual stack cluster, we would see an IPv4 and IPv6 range in there. Now, if we compare that to Cilium's default, we already can see the difference in the resource type, because there we need to do a kubectl describe Cilium node, which is a Cilium owned and maintained custom resource. It has plenty of details for each specific node, and there's such a resource per node. What we also see there is that it has a podsiders field, and this one is set to a completely different range. And it's this case set to 10.0.2.0/24. And to understand where does this come from, we need to have a look at the Cilium default Helm values, which we see here, and that's essentially the relevant section. That's the IPAM section, in which we can see Cilium's default value. So that's what you get if you just do a Cilium install on top of your cluster. We already see that the mode is set to cluster pool, sometimes also referred to as cluster scope. And this is combined with the 10.0.0.0/8 IPv4 range, which is used for actual pod IP assignments. Now, what's also configured there is the cluster pool IPv4 mask size, which is set to 24. And that's basically the range size, which is taken from this /8 range and assigned to each individual node. And every node does then do the IP assignment through the CNI from this particular range that is kind of assigned to this particular node. Like for IPv6, we have the same principle, but there we are using a 104 IP range and take out /120 ranges per node. In the end, in both cases, this leaves us 8 bits for pod IPs, which essentially means we can have up to 256 IPs available. Now, what we've just seen are essentially those first two IPAM modes that Cilium offers. And as you can also see on the more right-hand side of this table, Cilium offers way more IPAM modes, but the other ones are most often cloud-specific because they are kind of intended to be used with a direct cloud integration. Now let's focus a little bit more on the first two columns with the data. The Kubernetes host scope mode. There we already see on the third line that the site or configuration itself is done by Kubernetes, while for the cluster scope, we see that is managed by Cilium. And that's already the reason why we have different IP ranges if we just take the defaults. Now, I would like to share a bit more insights into the Cilium node custom resource definition, as it's a pretty essential one for Cilium, not only for pod IP assignments, but also for other things, as for example, the health endpoint, as we see there on line 20, and also the Cilium internal IP. And both of those IPs are also taken from within this /24 range that is assigned to each node, which essentially results in 2 IPs less that we can actually use for pod IP addresses. Now we can also dig a little bit further and kubectl exec into Cilium agent pod, and from there we can list all the IPs that are currently known to this node by using Cilium debug IP list, and preferably combined with a pipe grep something, because the list can be quite long depending on how many pods you have within your cluster. Now there we beautifully see on line 10 and 11 those 2 IPs that we've just seen before here on line 20 and 13. So those IPs are kind of used for those 2 special purposes, and basically you can't use them for other pods because they're simply quite crucial to how Cilium is actually function. The first one, the reserved one, is for the health endpoint checking, which is enabled by default. And you can also have a look at Cilium's health, especially its health related to like remote node reachability. And that's done by, again, kubectl exec into the pod and then issue as Cilium health status -- verbose, which provides you this output here. We see for each remote node, the Cilium agent is doing basically 4 different health checks. The first 2 are for host connectivity, so it essentially means Cilium itself is checking if the underlay network is actually healthy and the remote node is properly reachable for HTTP and ICMP. It also shows you round trip times, and it would also show you errors and so on. In addition to that, that's where this reserved health IP actually comes into play. We have endpoint connectivity health checks to the health endpoints or health IPs of the remote nodes. And by using those two different types of health checks, we have the health from the underlay and we have the health from the overlay, because a pretty common architecture when deploying Cilium is to use a so-called overlay, which can either be based on VXLAN or Geneve, and the pod traffic is then actually routed through this or those tunnels to all the remote nodes. And because of that, it's super helpful to have both health checks, as sometimes there's an issue in the underlay, which obviously also affects the overlay. But even worse are the issues where the underlay is just fine. However, the overlay isn't working, so one pod on one node doesn't even reach the other pod on another node. Now, the other reserved IP is used for the Cilium host itself, so essentially for the Kubernetes node where the Cilium agent is running on. And this one is even more critical to Cilium, as it is used for basically all kinds of routing. So, for example, every pod that is running on this particular node here is using this IP 10.0.2.156 as its default gateway. That essentially means every pod that is on the same node does always use this IP as its default gateway to send traffic either to pods on the same node, to send pods on a remote node, or perhaps even via masquerading netting to the outside world. Now, through this interface, which is called Cilium host, Cilium itself also does basically the setup of the VXLAN tunnels or the Geneve tunnels to the remote nodes, and that's what we essentially see here on line 13 and 14, because there we have the /24 ranges from the pod siders of the remote nodes. Now here a few best practices for Cilium IPAM or IP address management in general. First of all, whenever you configure a cluster, please be aware of the Cilium IPAM mode you choose, that you do not mix those things up with what we've seen before. For example, you set the pod sider range on your Kubernetes flavor, and at the same time you're using something different within Cilium. Choose either mode and stick to this one. Then if you go with the cluster pool mode, which is essentially the mode fully managed by Cilium, be aware that by default it takes the full class A IPv4 range, the 10.0.0.0/8, which might cause an overlap with existing IP addresses within your network. So preferably you are setting this to, let's say, at least the /16 range that isn't used somewhere else within your network. Otherwise, there's a fair chance that you run into connectivity issues, especially if you have pods or workloads inside your cluster that needs to reach IPs like actually outside of the cluster, somewhere in the underlay. However, as this range might be reused within the cluster, it might not even end up in the underlay. And second there, we also seen that by default, it sets the basically the CIDR size or range to a /24, which might be way too big for your actual cluster. So first of all, make sure you align this with your kubelets max pod configuration, because this one is by default set to 110, at least with upstream Kubernetes. So most of the time, it doesn't even make sense to have up to 254 IPs available for pod assignments per node if the kubelet itself on this node is only able to run 110 pods, right? So we could, for example, reduce that to a /25. Also, if we compare those two sizes, so a /8 and the /24, we basically have 16 bits available for nodes, which is oftentimes, at least for all of the customers and Cilium deployments I know, it's way too large, because I've never seen a cluster having up to 55,000 nodes. Last but not least, I would like to highlight two pretty helpful metrics there. That's the Cilium IPAM capacity metric and the Cilium IPAM address metric. And both can be super helpful to spot potential shortcomings of IP addresses on specific nodes. So make sure you use them within your Grafana dashboards or build alerting based on that, for example, within your Prometheus. Let's talk about the second story, which I called, wait, eBPF maps are not infinite? Now, surprise, surprise, unfortunately, they are not. And before we dig into what this actually means, I would like to briefly mention what an eBPF map even is. An eBPF map is essentially a kernel internal construct that can be used by eBPF programs and user-based processes to cache, exchange, and basically just store data. And that's all within memory. So this whole map is always within your Linux host's memory. And it can, for example, be used for an eBPF proc that is hooked to a specific network eBPF hook within the kernel to create metrics, which are then later on scraped or kind of fetched by a user-space program, and then, for example, builds kind of alerting, monitoring, whatever based on that. There are different types of maps. For example, there are hash maps, there are arrays, there are ring buffers, there are longest prefix match. So it highly depends on what kind of data you actually want to store in such a map. And I think overall there are 15 map types or something like that. Refer to the ebpf.io documentation if you want to learn more about those specifics. But as you may already know, Cilium itself is highly based on eBPF. And with that, it obviously also uses or leverages different types of eBPF maps. So for example, it uses eBPF maps for connection tracking, for netting, for network policy enforcement, for layer 4 load balancing within the cluster, and so on. Now, the critical part here could be something like this. And that's actually something we've seen multiple times, especially with large customers. And large customers essentially mean very large clusters. That's one case where this can easily happen, or just clusters with a lot, and by lot I really mean a lot of different network policies. So there we are speaking about thousands of different network policies to kind of probably implement a fully zero trust approach or something like that. Now, in this scenario here, that's based on my reproduction environment. So you can also kind of do that on your own by having a look at the publicly shared GitHub repository. But in the end, I just applied a very, very inefficient Cilium network policy, which caused this specific Cilium policy eBPF map to be fully maxed out within a few seconds. Now, to understand where does this come from, we probably need to understand how such an eBPF map is created. And that's essentially through such a struct that you see here, where we see on line 3 the very key part, which is called max entries. So whenever you create an eBPF map, you need to already predefine how big this map should actually be. And this is also then reflected within your memory usage. So don't just go all over it and just set it way too high, because otherwise the memory usage will suffer. Now, luckily, again, there are pretty helpful Cilium eBPF metrics in there. For example, there are Cilium eBPF map pressure. There's this map pressure metric, which is essentially a float value between 0 and 1, and it's essentially a percentage of the utilization of the regarding map. In addition, there's this Cilium BPF map ops total metric, which is especially helpful with the additional filter or label outcome equals fail, because this would indicate if Cilium fails to read or write to a specific map. So definitely make sure if you run a Cilium environment in production to keep an eye on those two metrics and preferably even automated alerting. To further understand like where does our kind of scenario coming from with those overflowing policy maps, we need first understand how Cilium is actually do network policy enforcement, and that's where Cilium identities come into play. That's essentially another Cilium abstraction, because as we all know, like pods are pretty ephemeral. Like their IPs can get changed like within a few seconds in case they get rescheduled on another node or even rescheduled in general. So we can't rely on IP addresses to do the actual network policy enforcement. And because of that, Cilium introduced the Cilium identities construct, which essentially abstracts uniquely labeled pods. And it's basically, it basically takes all the labels that are assigned to a specific pod, and it then generates a Cilium identity for each of those unique label sets. So here in this example, if we have role frontend trying to connect to role backend, we don't do any enforcement based on IP addresses. Cilium just does it based on the identities. Now, coming back to my reproduction with this very inefficient Cilium network policy, I wanted to actually show it to you and kind of give you some hints or like explanations why this one is very inefficient and you shouldn't apply it or apply similar constructs to your environment. So first of all, it selects all endpoints within this namespace where this policy is applied. Now that's there on line 7, the endpoint selector, which is empty, so it selects all endpoints within this namespace, which isn't a bad thing per se. That's kind of still a common thing. However, it gets even worse if we have another look at the line 10, where we see from entities cluster, which means Cilium needs to take care about all other remote entities within the cluster, and not only the ones within this namespace, for example. Now, in addition to that, we also see there on line 17 and 18 that we have a super large port range defined, which covers up to 9,000 ports. And on top of that, even worse, we have protocols set to any, which essentially means Cilium is kind of allowing traffic over those ports for UDP, for TCP, and for SCTP. Which essentially means it triples the usage, and with that it also triples the space that Cilium requires within the Cilium policy eBPF map to keep track of the allowed connections. Now, if you want to dig deeper, you can actually do that and have a look at how the map actually looks like. And again, use kubectl exec into the Cilium agent, and then use Cilium debug. Map get and then the map name. You can also do a Cilium debug map list to have an overview or all the maps, but here I only wanted to have the content of a single map, and to be more precise, I wanted to have the content of the map of the Cilium endpoint 83. Now what this 83 means, we have a look at that like in the next slide, but first of all I would like to cover there as an example line 8, because that's essentially what Cilium is allowing. It's allowing ingress connection, for example, for the source identity. In that case, it's a source identity because it's an ingress rule. In that case, for up to 16 ports, but it could also be like a single port. And it's using protocol TCP. Now, if you define a policy like we've seen before with any, we basically see the exact same line once again for UDP and once again for SCTP. And in the end, you also see some additional values. First of all, the column with all the zeros, they are all set to 0 because none of those rules are actually layer 7 policies, which means there's no additional DNS or HTTP-based enforcement. It's a plain layer 3, layer 4 enforcement policy, and with that, Cilium can do everything directly within eBPF, which is super efficient. Now, if it would have in addition to that, like filtering for specific domains or like specific HTTP verbs or HTTP endpoints, we would see a proxy port there, which is kind of hosted or like listening on the regarding Cilium DNS proxy or the Cilium Envoy proxy, depending on like what kind of filtering you configured in the policy as well. Last but not least, like there, let's take the 20 as an example. Overall, we have 24 bits available, but because our range is 16 ports, we have 2 to the power of 4 equals 16, so we need to wildcard 4 bits, which essentially means we need to deduct 4 bits from those 24 bits available, which results in this 20 over there. Now, you can correlate this information with, for example, the endpoint itself by running a Cilium debug endpoint list. So you have more details about the endpoint. And here on the right-hand side, you even have the specific labels that are set on this pod and are used to generate, like, first the endpoint itself, but also the Cilium identity, which is in the end taken for the network policy enforcement. Now, we also see the identifier of the Cilium identity, which is 85,000 something. And if we also want to look up the other, like the source identity from the left image on like the second column, that's this 98,000. We can also directly see like the other entity, which is allowed to communicate to our, in this case, other entity with the labels app, workers, and so on. Now here are a few best practices for eBPF map handling, as that's also super crucial, especially for large clusters. First of all, again, there are pretty helpful metrics there. Definitely make sure that you set up alerting based on that, on those metrics. Second, oftentimes it makes sense to kind of instruct Cilium about which labels it should care and about which label it shouldn't care. And that's done through a configuration called Cilium Identity Relevant Labels. And for example, it basically doesn't make sense at all for Cilium to like care about pod-specific labels if your intent is to do network policy enforcement based on network, based on namespace level. Like Cilium itself only needs to know the namespaces. It doesn't need to care about the pods within those namespaces. So you can get rid of quite a lot of different entities. And other than this, for example, you could also restrict some kind of randomly generated, or like you can set, or like you can configure it in a sense that Cilium would ignore highly unique label key value definitions, for example, from like pods that are started through jobs that sometimes have some kind of a pod hash or something. Oftentimes, like all of those jobs should be or like free or like taken care of the same way. So there's no need for Cilium to actually have a dedicated identity for each of those pods. Now, in addition, if you really need such or so many identities, again, there's an option to increase the limit, which is by default set to 16,000 entries for this particular policy map, but you can easily increase it to like 10 times this size, for example. Just be aware that it then also leads to a higher memory consumption. Last but not least, like the kind of the most relevant part there, like whenever a Cilium policy eBPF map is basically overloaded, so we have an eBPF map pressure situation, Cilium defaults to the behavior to allow all other traffic, which is most likely or oftentimes not what you actually want, because then suddenly like an endpoint can be reached even though it shouldn't, because there should be network policies. However, when Cilium does not have the capacity anymore within this eBPF map, it then basically has like a fail open or fail closed trigger, or like configuration. And you can override that by using the so-called policy lockdown mode. And if you do that, you basically are instructing Cilium to stop and drop all kind of incoming and outgoing traffic to this particular endpoint in case this particular endpoint's eBPF policy map is overloaded. Let's talk about the next story, which I call packet, where are you? Now, let's assume a pretty simple situations. In this case, we have a test client and a test server, and the test client is connecting to the test server on 2 different ports. Unfortunately, only one of those ports is working, and as we see, port 8443 isn't working. However, like within the test client itself, we just do a troubleshooting curl command, but we just get something like could not connect to server. Not super helpful. But we still see that on the working port, we actually get a valid reply. In this case, for example, we get our request returned back from the server. Now, how would you troubleshoot that? Perhaps by first starting to validate the manifests, the Kubernetes manifests you applied. For example, the Kubernetes cluster IP service that you basically put in front of the test server. So here we double check if like the service finds the endpoints, and we already see there on line 14 and 17 that everything looks good. Like the server is found, like the label selector is correct, the ports are found, so doesn't seem to be something wrong with the service itself. Perhaps there's a network policy which isn't allowing the traffic. Like from a network policy manifest standpoint, it looks good because we're allowing port 8080 and 8443 on the left-hand side in ingress direction and on the right-hand side in egress direction. That's also something to be aware of, that most of the time you need to allow your traffic in both directions. Now, perhaps it's a good idea to use something like TCP dump, as you may already know it from traditional Linux troubleshooting. In there, for the healthy port, you see a proper TCP three-way handshake. You see the SYN, SYNAC, ACK. You see a FIN, FINAC, ACK, and so on, so all good. You even see the TCP, the HTTP headers in there. However, for the not working port, you're only seeing a SYN, TCP SYN sent from the client to the server, and you only see a TCP reset. Now, let's double check if the network policy enforcement is really sufficient. And luckily, there's a super powerful tool provided by Cilium that comes out of the box, which is called Cilium and Hubble. And this one does not only show you like a TCP dump or T-Shark output, it's also enriched with Kubernetes metadata. So you actually see namespace names, pod names, you see the Cilium identities, you see things like if it's allowed there on line 2 in egress direction, or if it's denied, you would also see a deny. And beautifully, you also see not only in egress, but also ingress direction, and then followed by a proper TCP handshake communication. So here, for our working port, all good. However, if you compare that to our not working port, we already have the verification that it's for sure not a Cilium network policy issue, because for both sides, for egress and ingress, we see an allowed there. However, we still see the TCP reset at the bottom. Now, unfortunately, a TCP reset can have multiple reasons. For example, it could be a firewall that is in between, that's actively rejecting but not dropping the traffic. It could be a misbehavior in the destination application. It could be a misbehavior in the TCP or in the operating system stack of the target system. And it could also be something like there's simply no application listening on this port, or it could also be a middle box like a load balancer or a proxy that is misbehaving. So basically, this doesn't help us much. So luckily, there's another eBPF-powered tool for network troubleshooting, especially for network troubleshooting within the Linux kernel. Now, this tool is called Packet Where Are You? And is essentially showing you nicely where a package within the Linux kernel traverses through the different layers. You see things like net filter hooks, you see routing, you see masquerading, and so on. And in this example, we just set an IP table rule to drop specific destination traffic. And if we then test it, but at the same time spawn up a packet where are you instance filtering for this particular flow, we directly see the actual reason why it's dropped somewhere within your Linux kernel. In this case, we have a drop reason, SKB drop reason, net filter drop, because we actually have an IP table rule which is implemented within the net filter framework within the Linux kernel. And yeah, with that, it's kind of already the proper explanation why a package is dropped. Now, if you apply the same principle to our troubleshooting scenario from before, we see that we get a lot of different output. So that's why I needed to truncate or like cut out a few lines, a few hundred lines, I guess. But in the end, you see the actual drop reason, which is super helpful and great visibility, in my opinion, because we see SKB drop reason no socket. And by the way, SKB basically stands for socket buffer, and it's essentially the metadata structure which is kind of created within the Linux kernel for every single network network packet, and it's this metadata kind of data structure which is modified when a package traverses through the Linux networking stack. So to further understand what this actually means, we can have a look at the Linux kernel code. And in the end there, on line 141, it shows us no valid socket that can be used. Kind of simple as that. Let's verify this by using something like kubectl debug or kubectl exec, depending on if you have like a shell and so on within your target application. Here we're using show socket, and we see that the port 8443 isn't even listening, so it's for sure an application failure. Now here are a few best practices for network connection troubleshooting. And first of all, my personal recommendation, always start troubleshooting with Cilium Hubble. I personally prefer Cilium Hubble CLI over the UI, as it's a bit more powerful, especially with regards to its filtering capabilities. It basically shows you TCP dump output on steroids because it's enriched with Kubernetes metadata. It's showing you TCP states. It's showing you network policy allows or denies. And in addition, always super helpful are Kubernetes debugging containers, which you can attach either to your workloads, to specific pods, or even better, sometimes even more helpful for network troubleshooting, you can also start such a pod directly on the node. So you can directly use them for host networking troubleshooting in case you have or you suspect an network underlay connectivity issue. And last but not least, as a tool of last resort, packet where are you, always super helpful if it gets really tricky. And pro tip there, if the output is overwhelming to you, what I personally also have, there are common AI models that explain you pretty well how to read it and like what the actual root cause is. And with that, I'm already at the end of this presentation. Unfortunately, we only have had time to show 3 stories. Again, there's a 4th story with all the details in the slides. Please feel free to have a look at the slides. And if you want to learn more about eBPF map pressure or packet where are you, there are some other talks from colleagues. And with that, thanks a lot for your attention.
From ContainerDays Hamburg, this video is proudly presented by DuxIT.